So we're going to start off by defining three topics that are all getting us to the percent yield. So we'll define theoretical, actual, and percent yield. And then we'll calculate these for non-limiting reagent questions. So in this lecture, we're just going to focus on the non-limiting reagent questions. Once you learn about limiting reagents, you should also be able to connect the two ideas together, but we're not going to cover that in this particular lecture or really in any of the lectures, as the problems get relatively long and it's just combining two topics. But make sure that you can do it. And if you need help, just come talk to me. So first off, what is theoretical yield? Theoretical yield is actually something that we've been talking about and we just haven't called it that. So this is the amount of the product that is created if the reaction is 100% efficient and all of the limiting reagent is used up. So if everything goes as planned, the amount of product that you get is the theoretical yield. In actuality, this doesn't usually happen though, and that's why we have this thing called a percent yield. So we're going to just take some silly examples to talk through the idea behind this. So for the theoretical yield, let's say that a student is making appetizers. Each one must have exactly one cracker and one slice of cheese. This particular student is not a gourmet chef. So we have a package with lots of crackers, way more crackers than we could ever need, but you only have 20 slices of cheese. So we have 100 crackers, that's what we're going to say the package had, and 20 slices of cheese. How many crackers, cheese appetizers can we make? Well, we can only make 20, because at that point we run out of cheese. So our theoretical yield here is 20. However, actual yield comes into play when we're dealing with real chemical reactions where problems happen. So this is the amount of product that you actually create after human error, problems with efficiency, all sorts of things that you'll learn about next year that cause this. This is what we actually get. So let's take a slightly different example. We have the same student who's making the same appetizers with the same numbers, but a dog comes into play now, and it gets 2 of the slices of cheese. So now we can't make 20 crackers anymore, we only get 18. So even though we should have had enough to be able to get 20 appetizers, something went wrong, something happened, and we end up with 18. So percent yield then tells us the comparison between what we should have gotten and what we actually got. And this is really, really useful when we're dealing with chemistry to know, because if you want a certain amount of product, you want 100 grams of product when you get all done, but your reaction is only, let's say, 50% efficient, if you don't put enough reactants in there to be able to make double what you think you need, you're not going to have enough at the end. And so this is really important to know. So our percent yield is our actual over our theoretical times by 100%. So in this case, with our little doggy example, we should have gotten 20, but in actuality, we only got 18, and so we had a 90% yield. Your first year of lab, you'll generally be doing a lot of things that human error comes into play and will lower your percent yield. But there are also many reactions where even if everything is done perfectly and no dogs are involved, you still end up getting a lower percent yield than 100%. It's a relatively common situation, and so oftentimes you'll report your percent yield regularly for the sake of future people who want to make these chemical reactions. So now let's do a chemical equation. Here we have a metabolic reaction where we have an unlimited amount of oxygen, or that's what we're assuming, and we have a 1 gram sample of sugar being metabolized to produce an amount of CO2. It produces 0.98 grams, and I want to know the percent yield of this. So we know that our percent yield is actual over theoretical times by 100%. And I tell you the actual yield. I tell you that we get 0.98 grams of CO2. So now we have to figure out the theoretical yield. And we do that using our conversion factors that we learned about. So if we start off with 1 gram of our sugar, we need to convert that into moles to get to moles of carbon dioxide. So first, we use our molar mass of the sugar. From here, we use our mole ratio, so we know that we have 6 moles of carbon dioxide to every 1 mole of glucose. And then from there, we can use our grams of carbon dioxide per mole, again from the periodic table, to get to our grams of carbon dioxide. That's how much we'd create if every little bit of this was used up and everything was 100% efficient and there was no side products or no side reactions going on. So this we now fill into here to get our final answer of 67%. You can kind of see between the two of these how you would do this if you have a limiting reactant as well. It just adds about 3 extra steps because you have to do this for each problem. Find the limiting reactant first and then do this. So in summary, we have our theoretical yield, which is the amount of product that is created if the reaction is 100% efficient and all of the limiting reagent is used up. Whereas our actual yield is the amount of product that we actually get after everything is said and done. And our percent yield, like all percents, are actual over theoretical times by 100%.